Today let's talk about well-ordering principle and strong induction. Well-ordering principle. It is an intuitive statement which says that every non-empty subset T of n has a least element, where n is the set of natural numbers. Proof. Let Pn be the statement that any set of natural numbers containing a natural number smaller than or equal to n has a least element. If a set S of natural numbers containing a natural number smaller than or equal to 1, then S is the set containing 1, and the least element of S is 1, so P1 is true. Let m be a natural number. Suppose Pm is true, that is, any set of natural numbers containing a natural number smaller than or equal to m has a least element. Let C be any subset of n containing a natural number smaller than or equal to n plus 1. Case 1. If C has no element less than n plus 1, then n plus 1 is the least element of C, and we are done. Case 2. Suppose there is a natural number y in C such that y is smaller than n plus 1. Suppose y is greater than m, then m is smaller than y, which is smaller than n plus 1. Proven in the last video, we know that there is no natural number between m and n plus 1. Contradiction arises. So y is smaller than or equal to m. By induction hypothesis, C has a least element. In both cases, C has a least element, so Pn plus 1 is true. By the principle of mathematical induction, Pn is true for any natural number n. Let T be a subset of n which is non-empty. There is some k in T since T is non-empty. Then T contains a natural number smaller than or equal to k, which is just k itself. Then T has a least element, as Pk is true. Corollary. Every non-empty subset S of n union the set containing 0 has a least element, where n union the set containing 0 is the set of non-negative integers. Proof. Let S be the subset of n union the set containing 0 be a non-empty set. Case 1. If 0 belongs to S, then 0 is the least element. Case 2. Suppose 0 does not belong to S. Assume X belongs to S, then X belongs to n union the set containing 0, since S is a subset of n union the set containing 0. As 0 does not belong to S and X belongs to S, we have X is not 0, so X is a natural number. Therefore, S is a subset of the set of natural numbers. By a well-ordering principle, S has a least element. In both cases, S has a least element, and we are done. Note that some people refer to this corollary, which is about the set of non-negative integers, as the well-ordering principle. Principle of strong induction. Let Qn be the predicate with variable n. Suppose Q1 is true. Further suppose that for any natural number k, if Q1, Q2, blah 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 to Qk are true, then Qk plus 1 is true. Then Qn is true for any natural number n. To distinguish strong induction from the ordinary induction we discussed before, we sometimes call it weak induction. Proof. Let Pn be the statement that Q1, Q2 up to Qn are true. P1 is true since Q1 is true. Let K be a natural number. Suppose Pk is true, then Q1, Q2 up to Qk are true. Then Qk plus 1 is true by assumption. Then Pk plus 1 is true. By the principle of weak induction, Pm is true for any natural number n. Then Qn is true for any natural number n. Applications. The well-ordering principles can be used to prove the division algorithm, also known as the division theorem. Strong induction can be used to prove the existing part of the fundamental theorem of arithmetic. We will cover them in the topic of number theory. This is the end of the video. If you find my video interesting, Please consider subscribing to my channel, liking my videos, and commenting down below. See you in the next video. Thank you.